In the last reading, we were dealing with the first stage of the scientific revolution, the stage where the old ideas of the movement of the heavens were being attacked, and an entirely different idea, if not an entirely new one, was being put forward by Copernicus. That was in the middle of the 16th century, around the year 1540. This idea was taken up by certain other astronomers, and on the basis of the Copernican picture, another set of astronomical tables was drawn, the so-called Prussian tables, indicating, as it were, where the center of science was moving. Prussia in those days extended further east than it does now, and the area where Copernicus worked was called alternately Prussia or Poland. Astronomers still went on using the old methods, but they had to work much more accurately if their work was to be of practical use in navigation. Tycho Brahe, whose observatory is at Uraniborg. The older observations were perforce limited because of the scale and apparatus available and because of the inaccuracies of the observers. One of the maritime nations, a halfway nation, that of Denmark, happened to be enjoying a period of extreme prosperity at the time. It had become prosperous by taking tolls on all the traffic that was going in and out of the Baltic through the Sound. Of course, the reigning king of Denmark at the time was Frederick II, and one of his noblemen was Tycho Brahe, who had the privilege of a good slice out of the toll of the Baltic, who was also given an island in the south on which he set up what was the first scientific institution of modern times, called Uraniborg, or Heaven's Castle. Unfortunately, Tycho Brahe was rather a hard man. Apart from being a good scientist, he was very quarrelsome, and he became involved in a duel, had his nose cut off, and had to wear a silver nose for the rest of his life. He was a very hard person on his tenants, so that the moment he was out of Uraniborg, the local peasantry tore it down and took everything away. Of course, there was absolutely nothing left for subsequent historians. We have only a picture of it which shows what an observatory was like in those days. Of course, it was a typical nobleman's house with a few special scientific additions. The observatory part had 4 places from which to watch the stars, and another 2 higher up. The rest were Tycho Brahe's own apartments, except for the basement, which was entirely devoted to laboratories. The chemical laboratories can be clearly seen. All kinds of sciences were carried on together there, and Tycho had, as I have said, a considerable amount of money with which to do so, and after some difficulty he was able to get very useful assistance. Now, the revolution in the understanding of the world that was being effected at this time, for example, we could think of the old cosmology as being the old Aristotelian cosmology, illustrated in the Gemma Phrysis' revision, Cosmographia of 1539, of Peter Apian's Cosmographius Liber, 1524. Which at the center there is the earth with the animals and plants on it, and the elements, earth, water, air, and fire, and then the spheres and the moon and the sun, etc. Then outside the zodiac at the top, the 7th heaven, or the sky, the dwelling place of God, or the divine, and all the elect. For of course, a very nice closed world, but with a different center. That is all. Tycho Brahe knew of Copernicus's work, but did not choose to follow it all the way. He had a translation of it, which preserved the central position of the earth, but left everything else where Copernicus had placed it. That is, he said the moon and the sun went around the earth, but the planets went around the sun. This made sense geometrically, but not physically, because it still required the whole system to move around the earth once a day. However, Brahe was more concerned with getting very accurate measurements, and for that he had a set of instruments which are not very different in principle from earlier ones, but they were larger, of course. The observations were repeated with them more often and carried on for a longer time, and the results were extremely detailed. He had trouble in getting suitable assistance for this particular kind of work, but he did manage to get hold of a rather wild young German called Johann Kepler, who worked for him for a few years. In the late 16th century, 1588, King Frederick II died, and protectors were elected in order to govern Denmark during the minority of the young prince, Christian IV. Of course, afterwards, Tycho Brahe, who had half had always been disliked by his fellow aristocrats, began to lose favor with the court, which had never been much interested in his work. But in 1596, he was deprived of his appointments and King Christian's protection. The next year, he left Uraniborg. He brought the whole observatory to a standstill and transferred the instruments elsewhere. In the year 1599, he became chief mathematicus of the Emperor of Austria, Rudolf II. This was a very queer emperor who never went to Vienna but lived all his time in Prague. He set up not only an astronomical observatory but remarkable alchemical laboratories that are still in existence, and he harried his mathematicus to provide him with all the necessary horoscopes, of course. But meanwhile, Tycho Brahe left all his observations and records. There was a lot of trouble about this to his assistant, Kepler. Of course, Kepler had great difficulty in getting them away from the family, because in those days they still believed that the only possible successor to an astronomer was obviously his son, and the accumulated records should all be kept in the family. But Tycho Brahe's sons were almost incapable of mathematics, much less of astronomy, and they agreed to hand everything over, I think for some consideration, to Johannes Kepler. It did not always happen. Of course, for instance, in France, the astronomer Cassini was followed by his son Cassini II and Cassini III and Cassini IV. For more than 120 years, they were hereditary astronomers of the kings of France, and they were, as it happens, all very good astronomers. Now we move on to Johann Kepler. We can think about Kepler's first attempt to interpret planetary motion. We look at his De Harmonis Mundi that he wrote in Linz in the year 1619. The fundamental change was to be effected not by Tycho Brahe, except that he was absolutely essential in providing the observations, but by Kepler, who interpreted them. Kepler's main purpose was to make sense of the picture. He could see that the planets went around. He could even venture measurements based on the Copernicus system, which were possible by that time, although not previously. Mutual distances could be measured, and one could see exactly how the planets did go around. Kepler was able to sense that the whole thing must fit into a system of some sort, that it must have some kind of harmony. His first effort on that was typically along the Greek lines. He believed that the successive orbits of the different planets were arranged so as to fit a set of polyhedra, one inscribed inside the other. There were 5 planets, there were 5 regular solids. It seemed obvious that the 5 planets must be related to the 5 regular solids, just as the Greeks had considered that the 5 elements were relative to the 5 regular solids. A kind of analogical logic. But in the center there was a icosahedron, or icosahedron around the icosahedron, a pentagonal dodecahedron, around that a tetrahedron, around that a cube. The cube fits into a sphere, and there you have the whole system. But it was not so very far wrong. The curious thing about Kepler's system was that despite this, it was wrong to a degree that the experiments or the observations would not allow. Nevertheless, Kepler became the father of modern theoretical as well as experimental physics, because he recognized that while you had perfect freedom in working out your theories, they had to fit the observations. Plato and other people produced theories, but when they found that the theories did not fit the observations, they merely thought it so much the worse for the observations. But in effect, they said there is an ideal world, and if the real world is bad, well, we must expect everything to be bad in a real world, so we will stick to ideal astronomy. But Kepler was not satisfied with this attitude. He spent a considerable amount of time and trouble over this and wrote a long book about it, which he called The Harmony of the World. He wrote that in 1619. Finally, however, he gave the whole thing up because he could not make theory fit the observations. Then he went back and took a second look at them, giving himself more trouble. And of course, the second look was to try and solve the problem of why the planets did not go around regularly, why they went around faster at some times and slower at others. And this had been explained in the old system by putting in such things as eccentrics and deference and other purely mathematical tricks in order to save what are called appearances. But you can always save appearances if you introduce sufficient constants. A new period of revolution could always be compiled out of a number of subperiods. But Kepler wanted something simple, and in a sense, he found it, but going a very long way around. And of course, if we look at some of his drawings that he wrote in his commentaries on the motion of Mars, He concentrated on this one planet, and of course it was on the most appropriate planet on which to concentrate because it is nearest external planet, as well as one which can be observed at all times. It has a period of about 2 to 3 in ratio to that of the Earth. Kepler tried various curves for its orbit, and none would fit. Conventional epicycles would fit, but they were not quite correct. They were 8 minutes out of arc out. Of course, in the past, 8 minutes of arc would not have mattered. No one could measure accurately enough to 8 minutes of arc. The sun's image would need to be divided into a number of parts because the sun is 30 minutes of arc, but Kepler's measurements, or rather Brahe's measurements, were too accurate to admit an error as great as 8 minutes of arc. And so if Kepler had not come until later, people would have continued to make measurements and make them very accurately without any theory. There is no reason why there should be a theory, although it helps in a way. It is possible to make more and more accurate observations without any theories at all, of course. However, if he had made more accurate observations, Kepler would not have succeeded because an elliptical orbit fitted the degree of accuracy of his observations. He decided that the planet Mars traveled in its chariot around the sun in an ellipse. And so the ellipse, which he developed as a certain proportion of the corresponding circle, for example, and the sun is shown at one focus, of course. But out of this, he derived his first law. This is a straight observational law. He had no idea that it could make any sense dynamically because there was no knowledge even then of dynamics. But observationally, it was a simple curve, a curve which had been studied by the Greeks, and next to it a circle, which was the simplest of concepts. So he stated that all planets must travel in elliptical orbits of which the sun is the focus, and he went on, of course, to show that the moon traveled in an elliptical orbit around the Earth as well. That was Kepler's first law, which pleased him very much for quite a long time, but he was impelled to look further. At that point, the idea of an elliptical orbit, which the sun as one center, immediately raised the question of how rapidly the planet moved around in orbit. Of course, here he showed that it did not move around at a uniform speed, but faster when the planet was nearer the sun and slower when it was further away. From that, he deduced that the actual speed that it moved was such that it described the equal areas in equal times. It at once solved the problem of the inequalities of the times taken in different seasons. Why, for instance, the summer, when the Earth is far away from the sun, was longer than the winter when it was closer. This may seem strange, that summer in the northern hemisphere was hotter, not because the sun was nearer, but because the Earth was exposed to the sun at higher altitudes and for longer days. Effectively, all that the second law meant was that the momentum of the Earth in its orbit was constant. In other words, the product of the velocity and the radius vector remained the same. And so far, Kepler had worked out from sheer observation the law of movement of a single planet, but to cover all the planets together, he needed to know the relation of the periods of rotation of the planets and their distance from the sun. This, he concluded after many years of work, was in the ratio of the square to the cube. In this way, he finished the complete description of the motion of the planets in quantitative terms. His solutions, in fact, contained all the material that was necessary in order to work out the laws of force of the planetary system and made sense of Copernicus's institutions. But before this could be accepted, the possibility of the system had to be established by direct observation. And this was to be the work of our next figure, Galileo Galilei. And so the next reading, we will talk about Galileo.